On the evening of June 9, 1972, the Black Hills of South Dakota settled into the familiar rhythm of early summer. The air held the day's warmth, moving slowly through stands of ponderosa pine that covered the slopes rising above narrow canyon floors. Below the tree line, where granite formations gave way to sedimentary rock, small creeks traced their usual paths through channels carved over millennia. Rapid City, population approximately 43,000, occupied the eastern edge of this landscape. The downtown district sat along Rapid Creek, a waterway that descended from the Black Hills through a series of steep-sided canyons before spreading across the valley floor. By evening, traffic along Mount Rushmore Road had begun to thin. Storefronts closed their doors. Residential neighborhoods extending south from the creek prepared for an ordinary Friday night. The geography surrounding the city formed a distinct pattern. To the west, the Black Hills rose abruptly from the Great Plains, creating a natural barrier that forced moisture-laden air upward. Canyon systems cut into this terrain at regular intervals, each one channeling runoff toward the main drainage arteries. Rapid Creek represented the primary collector for this network, gathering water from dozens of tributaries before passing through the city and continuing east toward the Cheyenne River. The creek itself measured modest in normal conditions, perhaps 30 to 50 feet wide through most of its urban reach, with depths rarely exceeding a few feet during summer flows. Its banks, lined with cottonwoods and willow, had become integrated into the city's recreational infrastructure. Parks occupied the floodplain. Residential development extended to within yards of the water's edge in several neighborhoods. Above the city, approximately 6 miles upstream, Canyon Lake Dam held back a reservoir created in the 1930s. The structure served multiple purposes: flood control, recreation, and water storage. Its presence had shaped development patterns for decades, creating a perceived buffer between the city and the hydrological forces gathering in the canyons above. As darkness approached, the only notable atmospheric feature was a slight increase in humidity. Cloud formations had begun developing over the higher elevations, though this pattern occurred regularly during the late spring and early summer months. No warnings had been issued. Weather forecasts predicted scattered thunderstorms, a common occurrence for the Black Hills in June. The city's infrastructure reflected its position at the base of the mountains. Bridges crossed the creek at regular intervals, most designed for the creek's typical flow characteristics. Storm sewers and culverts carried runoff from streets and parking areas into the main channel. The downtown area, built decades earlier, sat partially within what historical flood records would have identified as the natural floodplain, though such designations carried less regulatory weight in 1972 than they would in subsequent years. In the neighborhoods nearest the creek, areas with names like Marlowe Park and Meadowbrook, families settled into evening routines. Street lights illuminated residential blocks. Television antennas picked up signals from local stations. The creek, visible from backyards and bedroom windows, continued its normal flow, producing the low background sound that residents had learned to ignore. The Black Hills themselves remained unchanged, as they had for thousands of years. The granite core, the layered sedimentary formations, the drainage patterns, all continued functioning according to processes established long before human settlement. The steep topography that made the region visually striking also created conditions for rapid concentration of runoff. Channel gradients averaged 8 to 12% in the upper canyons, sufficient to generate significant flow velocity during heavy precipitation events. By nightfall, the city had grown quiet. The pulse of daytime activity had subsided. What remained was the ordinary stillness of a small city in the northern plains, positioned at the interface between mountains and grassland, between the forces that shape terrain over geological time and the structures humans build in the present. The watershed feeding Rapid Creek encompassed approximately 410 square miles of the eastern Black Hills. This drainage basin collected precipitation from elevations exceeding 7,000 feet and funneled it through a convergent network of streams and tributaries. The main channel descended roughly 3,000 feet over its 40-mile length, creating hydraulic conditions capable of moving large volumes of water in compressed time periods. The creek's path through Rapid City followed what geologists recognized as an alluvial fan, a depositional feature formed by sediment carried from the mountains and spread across the valley floor. This fan, built over thousands of years, represented the creek's natural tendency to shift its course during high-water events. Historical records, though limited, suggested the creek had occupied multiple channels across this fan in the past. By 1972, human infrastructure had constrained these natural processes. Development covered much of the floodplain. Homes, businesses, and transportation networks occupied areas that the creek had historically used during periods of elevated flow. The channel itself had been informally modified in places, straightened, narrowed, and reinforced with ad hoc measures that reflected local needs rather than comprehensive hydrological planning. Canyon Lake Dam, completed in 1935, represented the most significant human intervention in the watershed. The earthen structure stood approximately 60 feet high and stretched 350 feet across the canyon. Its spillway, designed to handle overflow during flood conditions, could discharge approximately 1,200 cubic feet per second, a capacity based on historical flow data available at the time of construction. The reservoir behind the dam held roughly 1,500 acre-feet of water at normal pool level. Downstream from the dam, the creek passed through a narrow canyon section before emerging onto the more developed terrain. This canyon acted as a natural bottleneck, concentrating flow and increasing velocity. Where the creek entered the city proper, its channel widened somewhat, though development had encroached to the point that effective floodplain width measured less than what the natural topography would suggest. Infrastructure crossing the creek included more than 20 bridges and culverts of varying design and capacity. Many dated from earlier decades and reflected engineering standards that had not accounted for extreme hydrological events. Bridge piers and abutments created obstructions to flow. Culverts, designed primarily for ordinary conditions, could become choke points when debris-laden water attempted to pass through. The neighborhoods closest to the creek, Merlot Park, Meadowbrook, and sections of central Rapid City, occupied what hydrological analysis would classify as the 100-year floodplain, though comprehensive floodplain mapping did not exist for the area in 1972. Building codes did not prohibit construction in these zones. Property values in some creek-adjacent areas were actually elevated due to the perceived amenity of proximity to water. Urban storm drainage systems, designed to handle rainfall from impervious surfaces, connected directly to the creek through a network of pipes and channels. During normal conditions, this system functioned adequately. Under high-flow scenarios, however, these connections could reverse, allowing water to back up into streets and low-lying areas. On June 9, atmospheric conditions over the Black Hills began showing characteristics that meteorologists would later recognize as conducive to extreme precipitation. A low-pressure system had stalled over the region, drawing moisture from the south. Upper-level winds had weakened, reducing the system's forward motion. The topography of the Black Hills created additional lift as air masses moved westward, forcing moisture to rise and cool rapidly. By late afternoon, radar installations at Ellsworth Air Force Base detected the first substantial thunderstorm cells forming over the higher elevations. These cells, initially scattered, began to organize into a more persistent pattern. Rainfall started as intermittent showers but gradually intensified as individual storms merged, and the overall system became more stationary. Ground observations recorded rain beginning in the upper watershed around 6:00 p.m. Initial rates measured moderate, perhaps a quarter to half an inch per hour, but the rain showed no signs of the usual evening weakening that often occurred with mountain thunderstorms. Instead, the precipitation continued with consistent intensity, and in some locations appeared to be increasing. The creek responded as its hydraulic characteristics dictated. Small tributaries in the upper canyons began rising first, their steep gradients translating rainfall directly into increased flow. The main channel received this influx and began to swell, though at this stage, water levels remained within the normal range of variability. Residents familiar with the creek knew it could rise several feet during summer storms and typically recede within hours. By 8:00 p.m., however, the pattern had become less typical. Rain continued falling across the entire upper watershed with unusual persistence. Weather stations in the Black Hills recorded rainfall rates approaching 2 inches per hour, well above what historical records suggested was normal for the region. The moisture showed no indication of diminishing. The storm system, rather than progressing eastward as most systems did, remained anchored over the same terrain, continuing to draw moisture and convert it into precipitation. The watershed, saturated by earlier spring rains, offered limited capacity for absorption. Runoff coefficients increased as soil moisture approached saturation. Water that would normally infiltrate instead moved directly into stream channels. The convergent nature of the drainage network, dozens of small tributaries feeding into progressively larger streams, began to amplify the effect. Between 8:00 p.m. and midnight on June 9, meteorological conditions over the Black Hills established a pattern that would persist for the next 6 hours. The low-pressure system anchored itself over the region, held in place by high-pressure zones to the north and south. Upper-level winds, which would normally steer weather systems across the plains, had diminished to the point of ineffectiveness. The result was a stationary supercell, a massive, rotating thunderstorm complex that remained fixed over the same terrain. Radar imagery from Ellsworth Air Force Base showed a continuous band of extreme precipitation extending across the upper Rapid Creek watershed. Echo intensities indicated rainfall rates that exceeded the measurement capabilities of available instruments. Later analysis, using rain gauges that survived the event, would estimate peak rates between 6 and 12 inches per hour in some locations, levels rarely recorded anywhere in the continental United States. The sensory experience within the storm zone was one of overwhelming persistence. Thunder rolled continuously, not as distinct claps but as a sustained rumble that seemed to emanate from the clouds themselves. Lightning illuminated canyon walls at irregular intervals, revealing sheets of rain moving almost horizontally in places where wind funneled through narrow passes. Visibility diminished to near zero. The sound of rain striking rock, vegetation, and water became a pervasive white noise that drowned out other sounds. In the upper canyons, small creeks transformed rapidly. Channels that normally carried a few cubic feet per second began moving hundreds, then thousands. Water spread beyond established banks, finding paths of least resistance through forest floors and along canyon bottoms. Trees and vegetation, undermined by the force of flow, toppled into the water and began moving downstream, adding mass and destructive potential to the advancing flood. Rapid Creek's main channel received this concentrated inflow from multiple tributaries simultaneously. Hydrological gauging stations, where they existed, recorded flow increases that climbed exponentially. At the Canyon Lake Dam, operators observed reservoir levels rising at unprecedented rates. Inflow exceeded anything in the facility's operational history. The spillway, designed to handle 1,200 cubic feet per second, began discharging at full capacity, but this proved insufficient to prevent the reservoir level from continuing to rise. By 10:00 p.m., water in Canyon Lake had risen several feet above normal pool elevation. The spillway operated at maximum output, but the differential between inflow and outflow continued to increase. Reservoir storage, which under normal conditions provided a buffer between upstream rainfall and downstream flow, was being consumed rapidly. The dam's earthen structure, built to specific tolerances and loading conditions, began experiencing hydraulic forces beyond its design parameters. Below the dam, the creek's channel carried the spillway discharge plus continued input from tributaries that entered downstream. Flow depths increased from typical summer levels of 1 to 2 feet to 6 feet, then 8, then more. Velocity accelerated as the gradient drove water downslope. The characteristic pattern of mountain stream flow, turbulent, boulder-strewn, irregular, gave way to a more unified hydraulic force that pushed against any obstruction. Small bridges and culverts in the canyon section below the dam encountered flow conditions they had never experienced. Debris, primarily trees and brush stripped from upstream banks, began accumulating against structural members. This debris created temporary dams that raised water levels further, increased hydraulic pressure, and in several cases led to sudden structural failures. When culverts plugged or bridges gave way, the temporarily impounded water released in surges that propagated downstream, adding to the complexity of the flood wave. Road access through the canyons became impossible. Water overtopped highway surfaces in multiple locations. In some areas, the road itself began to fail, undercut by water flowing beneath the pavement. Emergency personnel attempting to reach upstream communities found routes blocked, communications limited to radio transmissions that conveyed increasing urgency but limited specific information. Rainfall totals, measured at stations that remained operational, exceeded 10 inches by midnight in parts of the upper watershed. Some locations would ultimately record 15 inches or more over the 12-hour period, a rainfall amount that exceeded the 100-year, 24-hour precipitation estimate for the region. The fact that this occurred over a much shorter duration made the hydraulic impact even more severe. At Canyon Lake Dam, operators faced a decision matrix constrained by physics. The reservoir could only absorb a finite volume of additional water. The spillway could only discharge at its maximum rate. Inflow from the storm continued unabated. The only question was whether the dam would overtop before inflow decreased, and if overtopping occurred, whether the structure could withstand the resulting erosion. By 11:00 p.m., the answer had become apparent. Water began flowing over the crest of the dam, initially in a thin sheet, then deepening as reservoir level continued to rise. The earthen embankment not designed for overtopping began to erode. Soil particles suspended in the overflow, then larger aggregates, then entire sections of the downstream face. The process, once initiated, accelerated according to well-understood principles of hydraulic erosion. Within 30 minutes, a breach had formed. The reservoir, containing millions of gallons of water under hydrostatic pressure, began to release. The outflow transitioned from controlled discharge through the spillway to uncontrolled release through an expanding breach in the dam structure. The volume of water moving downstream increased by orders of magnitude in a matter of minutes. The structural failure of Canyon Lake Dam occurred in progressive stages between 11:00 p.m. on June 9 and 12:30 a.m. on June 10. Initial overtopping created localized erosion on the downstream face of the earthen embankment. Water moving over the crest, even at shallow depths, possessed sufficient energy to dislodge soil particles and vegetation. This material washed downslope, undercutting the dam's crest and allowing deeper flow to pass over the structure. As erosion progressed, the breach widened horizontally and deepened vertically. The reservoir's water level, approximately 10 feet above normal pool elevation at the time overtopping began, created significant hydraulic head. This pressure differential accelerated the erosion process. Within the first 15 minutes, the breach had expanded from a few feet wide to more than 50 feet. The rate of erosion increased non-linearly as more water found the path of least resistance through the failing structure. By midnight, the breach had consumed a substantial portion of the dam. The remaining structure on either side experienced increased hydraulic loading as water flowed past at high velocity. Turbulence created by the partial breach caused additional scouring. The reservoir began draining at a rate far exceeding the spillway's design capacity. Estimates later suggested peak discharge through the breach may have reached 30,000 to 50,000 cubic feet per second, though precise measurement was impossible under the conditions. The water released from Canyon Lake represented more than just the reservoir's storage volume. It included continued inflow from upstream tributaries, which persisted as the storm maintained its position over the watershed. The resulting flood wave combined stored water, ongoing runoff, and accumulated debris into a single hydraulic mass, moving downstream through the narrow canyon below the dam. This wave encountered the natural bottleneck, where the canyon constricted before opening onto the more developed terrain. The confined space increased velocity and depth. Flow speeds likely exceeded 15 to 20 miles per hour in some sections, fast enough to move automobiles, dislodge structures, and transport massive amounts of debris. The sound of this movement, described in later accounts as resembling continuous thunder or a freight train, resulted from water striking obstacles, debris colliding, and air being compressed in confined spaces. As the flood wave advanced, it encountered infrastructure. The first major bridge below Canyon Lake Dam failed within minutes of the breach. Concrete abutments and steel support members, designed for loads measured in thousands of pounds, faced hydraulic forces measured in millions. The bridge deck lifted, twisted, and broke into sections that joined the debris field moving downstream. Similar failures occurred at subsequent crossing points, each collapse adding material to the advancing surge. Trees uprooted from canyon walls contributed significant mass to the debris. Ponderosa pines, some with trunk diameters exceeding 2 feet, became battering rams within the flow. These trees, along with smaller vegetation, formed temporary jams at bends in the canyon and around remaining structural elements. When these jams failed, as they inevitably did under continued hydraulic pressure, they released in sudden surges that sent walls of water and debris farther downstream. The flood wave reached the city limits of Rapid City shortly after 12:30 a.m. At this point, the flow had spread somewhat as the canyon opened onto flatter terrain, but the volume and velocity remained extreme. The creek's normal channel, perhaps 50 feet wide and 2 feet deep, now extended hundreds of feet across the floodplain, with depths exceeding 15 feet in the main flow path. Water moved at speeds that made resistance impossible for anything in its path. Neighborhoods on the western edge of the city received no effective warning. Power failures had occurred as the flood damaged transmission infrastructure. Emergency communication systems had limited capacity and incomplete information about the timing and magnitude of what was approaching. Most residents, asleep or preparing for sleep, had no indication that their proximity to the creek had become immediately life-threatening. The first structures encountered by the flood wave were primarily residential, wood frame houses on concrete foundations, many built decades earlier. The force of water against these structures exceeded their design loads by orders of magnitude. Walls collapsed, foundations shifted, entire buildings lifted from their moorings and disintegrated. The debris from these failures joined the advancing flood, increasing its destructive capacity as it progressed through the city. Vehicles parked near the creek or along streets in low-lying areas began to move. Cars and trucks, weighing thousands of pounds, floated briefly before being tumbled and carried downstream. Many came to rest against obstacles, other vehicles, trees, buildings, where they contributed to temporary debris dams that raised local water levels before failing and releasing additional surges. Utility infrastructure failed in sequence. Electrical distribution lines, both above and below ground, shorted and went dark. Natural gas lines, compromised by moving debris and shifting ground, began to leak. Water mains designed for internal pressure rather than external loading fractured. Communication lines, telephone cables, and emergency radio repeater stations lost function as their supporting infrastructure failed. The flood moved east through the city, following the natural topography of the ancient alluvial fan. The path was not uniform. Local variations in ground elevation channeled flow into specific areas, sparing some blocks while devastating others. The main surge generally followed the creek's established channel but spread hundreds of feet on either side, encompassing parks, residential areas, commercial districts, and transportation corridors. Bridge failures within the city followed the pattern established upstream. The Omaha Street Bridge collapsed early in the sequence. St. Joseph Street Bridge followed. Each failure eliminated an escape route and added material to the debris field. Bridges that remained standing often became collection points for debris, creating local backup that raised water levels and increased flooding in adjacent areas before the accumulated material shifted or the structure itself failed. By 1:00 a.m., the flood had reached downtown Rapid City. The commercial district, built in the creek's floodplain, received the full force of the flow. Storefronts imploded under hydraulic pressure. Display windows shattered. Merchandise and store fixtures joined the debris moving through streets at highway speeds. Multi-story buildings remained standing but sustained severe damage to ground floors. Parked vehicles piled against structures, driven by water moving faster than the current of most rivers. The darkness amplified the event's impact. Without artificial lighting, the flood remained largely invisible except where headlights from floating vehicles or emergency equipment briefly illuminated the water's surface. The sound, water, debris, collapsing structures provided the primary sensory input for those experiencing the event. The flood reached the heart of Rapid City during the early morning hours of June 10, moving through a landscape rendered nearly invisible by power outages and persistent rain. What little illumination existed came from vehicle headlights, emergency equipment, and occasional fires ignited by ruptured gas lines. The absence of ambient light transformed the flood into a largely auditory experience. The sustained roar of moving water, the percussion of debris striking obstacles, the grinding collapse of structures giving way under hydraulic pressure. The main flow path followed Rapid Creek's established channel through the downtown area, but water spread far beyond normal banks. Flow depths in the primary channel exceeded 15 feet in places, with velocity sufficient to maintain forward momentum despite the obstacles of urban infrastructure. On the floodplain extending south from the creek, water depths varied from a few inches at the margins to 10 feet or more where local topography created collection points. Neighborhoods that had been quiet residential blocks an hour earlier became active flood zones. Water entered homes through ground-level openings, doors, windows, foundation vents, then rose according to local hydraulic conditions. In some structures, water filled basements within minutes, then proceeded to ground floor levels. The speed of inundation varied based on elevation relative to the main flow, distance from the creek, and whether debris had created temporary damming upstream. The force exerted by moving water at these depths and velocities exceeded the structural capacity of most residential construction. Wood frame houses on concrete slab foundations experienced lateral loading that pushed walls inward or caused entire structures to shift off their foundations. Once structural integrity was compromised, buildings quickly disintegrated, contributing lumber, roofing materials, furniture, and appliances to the debris field. Mobile homes, common in several neighborhoods along the creek, proved particularly vulnerable. Their light weight and relatively weak attachment to foundations made them susceptible to flotation and displacement. Many were carried hundreds of feet from their original locations before lodging against more permanent structures or breaking apart entirely. Vehicles became mobile hazards within the flood. Cars and trucks parked on streets or in driveways entered the water column once depths exceeded 2 feet. At greater depths, complete flotation occurred. The flood carried these vehicles downstream, where they collided with buildings, other vehicles, and utility infrastructure. Some came to rest in improbable locations, stacked atop one another, embedded in storefronts, lodged against trees or bridge abutments. Utility systems throughout the affected area experienced cascading failures. The electrical grid, compromised by transmission line damage and substation flooding, ceased functioning in most of the city. Natural gas distribution lines, subjected to ground movement and impact from debris, developed leaks at numerous points. Several of these leaks ignited, creating fires that burned despite the water surrounding them. Water mains fractured where the flood scoured around underground pipes, or where surface loading exceeded the pipe's structural limits. Communication infrastructure suffered similar degradation. Telephone exchanges flooded. Emergency radio repeater stations lost power or sustained direct damage. The 911 system, such as it existed in 1972, became overwhelmed and then largely non-functional. Police and fire departments operated with incomplete information about the flood's extent and location of those requiring assistance. Response efforts faced immediate limitations. Emergency vehicles attempting to reach affected areas found routes blocked by water, debris, or failed roadway infrastructure. The darkness made assessment difficult. Water depths and flow velocity made approach dangerous. First responders arriving at the flood's margins could hear but not see most of what was occurring in the inundated zones. The storm system continued producing rain throughout these hours, though intensity had begun to decrease from peak levels. Precipitation still measured in inches per hour in parts of the watershed, sustaining inflow to the creek system. This ongoing contribution prevented any rapid recession of floodwaters. Areas inundated by the initial surge remained underwater, and in some locations, water levels continued to rise as flow from upstream tributaries maintained the flood's volume. Debris accumulation altered flow patterns throughout the city. Large piles formed where obstacles, remaining bridges, substantial buildings, terrain features, captured material moving in the flood. These accumulations could span hundreds of feet and contain thousands of tons of mixed debris, vehicles, trees, building materials, household goods, and sediment. The piles functioned as temporary dams, raising water levels upstream until structural failure or hydraulic piping allowed the impoundment to release. When these debris dams failed, secondary surges propagated downstream. These surges, though smaller than the initial flood wave from Canyon Lake Dam, still possessed sufficient force to cause additional damage. Buildings that had survived the first inundation faced renewed assault. Debris patterns shifted, sometimes clearing blockages but often creating new ones at different locations. The floodplain south of Rapid Creek experienced conditions distinct from the main channel but still severe. Water sheet flowed across this terrain, following subtle variations in ground elevation. Depths generally measured less than in the primary flow path, but the lateral extent was enormous. In some areas, flooding extended more than a half-mile from the creek's normal banks. This broad inundation affected neighborhoods that residents did not consider at risk, as the creek in normal conditions appeared distant and inconsequential. Industrial areas along the creek sustained damage that compounded the flood's impact. Fuel storage tanks ruptured, releasing petroleum products into the water. Chemical storage facilities were compromised. The mixing of these substances with floodwater created environmental hazards that would persist long after the water receded. Transportation infrastructure throughout the affected area became impassable. Streets filled with flowing water, debris, or sediment. Railroad tracks, where they crossed the floodplain, washed out or became buried under material deposited by the flood. The regional airport, located southeast of the main impact zone, remained operational but isolated as approach routes were severed. By 3:00 a.m., the flood had passed through the central city and continued its progress downstream. The creek's channel, now carrying multiple times its normal flow, continued to erode banks and transport sediment eastward toward the Cheyenne River. Communities downstream of Rapid City, though receiving advance warning, still faced significant flooding as the surge progressed through the watershed. Behind the flood's leading edge, water levels began a slow decline. The decrease was gradual, measured in inches per hour rather than feet, constrained by continued inflow from the watershed and by drainage limitations imposed by debris-choked channels and overwhelmed storm sewers. Areas with poor natural drainage remained inundated for hours after peak flow had passed. As dawn approached on June 10, the extent of debris accumulation became visible across Rapid City. The flood had transported and deposited material across several square miles of urban terrain, creating landscapes that bore little resemblance to the pre-flood geography. These debris fields represented one of the flood's most significant secondary impacts, complicating rescue operations and shaping the pattern of recovery for months afterward. The largest accumulations formed at structural obstacles that remained intact during the flood. Bridge abutments, substantial buildings, and terrain features created collection points where debris traveling in the floodwater came to rest. These piles, some exceeding 20 feet in height and covering areas measured in acres, contained heterogeneous mixtures of material: vehicles, trees, building components, household furnishings, and sediment compacted into masses held together by interlocking debris and mud. Vehicle accumulations formed distinct features within these debris fields. Cars and trucks, carried from parking areas and streets throughout the floodplain, came to rest in configurations that appeared random but reflected the hydraulics of the flood's final hours. In several locations, vehicles stacked 3 or 4 high, crushed under their own weight and the force of additional debris driven against them. Paint was scoured from metal surfaces. Windows were shattered. Interiors were packed with mud and smaller debris. Trees contributed substantial volume to the debris fields. Cottonwoods and willows from the creek's riparian zone, uprooted during the initial flood surge, traveled downstream as complete specimens, root balls, trunks, and canopies largely intact. Ponderosa pines from the upper canyons arrived stripped of branches and bark, their trunks acting as battering rams before becoming lodged in debris accumulations. The mass of woody debris in some fields exceeded that of any other material category. Building debris appeared throughout the affected area, though its concentration was highest in zones where structural destruction had been most complete. Lumber, roofing materials, siding, and insulation formed layers within debris piles. Entire wall sections, still framed and relatively intact, leaned against obstacles or lay flat on the ground. Concrete foundation blocks, displaced from their original positions, scattered across the floodplain. Household contents provided the most varied component of debris accumulations. Appliances, refrigerators, stoves, washing machines, appeared in improbable locations, often damaged beyond recognition. Furniture, clothing, books, and personal items mixed with mud and other debris. The randomness of these deposits, a sofa lodged in a tree, dishes scattered across a parking lot, photographs embedded in sediment, reflected the chaotic nature of the flood's transport mechanisms. Sediment deposition altered ground elevations throughout the affected area. In some locations, mud and sand accumulated to depths exceeding 3 feet, burying streets, yards, and ground floor interiors. This material, carried from upper watershed slopes and creek banks, ranged from fine silt to coarse gravel. When deposited in layers, it created stratigraphic sequences that recorded the flood's changing velocity and sediment-carrying capacity. The debris fields created immediate operational challenges for emergency response. Access roads into the most heavily damaged neighborhoods remained blocked by material that required heavy equipment to clear. Emergency vehicles that did reach the periphery of debris accumulations found further progress impossible. Foot traffic through the debris proved slow and hazardous, as unstable piles shifted under weight and sharp objects concealed by mud posed injury risks. Search and rescue operations faced limitations imposed by these conditions. Teams working through debris fields moved at a fraction of normal speed. Visual identification of structures, necessary for systematic search patterns, was difficult where debris covered landmarks and altered terrain. The presence of ruptured gas lines and the possibility of structural collapse added to the hazards. The debris fields also contained remains of those killed in the flood, though locating these individuals proved difficult given the extent of material deposited and the condition of human remains after transport through the flood. Systematic recovery operations would require weeks, constrained by the need to carefully excavate debris accumulations while maintaining safety protocols. Water velocity patterns during the flood determined where debris accumulated and where it was absent. Zones of highest velocity, typically in the main creek channel and along the primary flow path through the floodplain, had been scoured relatively clean. The erosive force of fast-moving water removed not only surface debris but also topsoil, vegetation, and in some cases, pavement and underlying base materials. These scoured zones appeared as linear features extending downstream from Canyon Lake Dam through the city. Adjacent to scoured zones, areas of deposition showed where velocity had decreased sufficiently for the water to release its sediment and debris load. The boundary between erosion and deposition often measured in tens of feet, creating a patchwork pattern across the floodplain. Understanding this pattern became essential for later reconstruction planning, as areas of deposition generally retained some subsurface infrastructure while scoured zones required complete rebuilding. Secondary debris dams, formed during the flood when material accumulated against obstacles, left distinctive signatures after water receded. These features appeared as linear piles extending upstream from the obstacle that had caused initial accumulation. The upstream face of these deposits showed layering that recorded progressive accumulation, while the downstream face often showed evidence of overflow or piping where water had found paths through or around the debris. Bridge sites presented particularly complex debris fields. At locations where bridges had failed, debris mixed with structural components from the bridges themselves: concrete, reinforcing steel, timber decking, guardrails. Where bridges remained standing, debris piled against upstream faces, often to heights exceeding the bridge deck. These accumulations would require careful removal to prevent further structural damage during cleanup operations. The downtown area, though built with more substantial structures that largely remained standing, contained extensive debris deposits at ground level. Storefronts opened directly onto layers of mud and material that had filled streets during the flood. Basements, accessible only after water pumping operations, contained compressed layers of sediment, debris, and damaged inventory that filled spaces from floor to ceiling in some cases. Industrial areas along the creek contributed specialized debris. Fuel from ruptured storage tanks formed films on water surfaces and coatings on other debris. Chemical containers, emptied by the flood or still partially full, scattered across the floodplain. Construction materials from lumberyards and supply businesses, sheets of plywood, bundles of rebar, pallets of concrete blocks, deposited wherever the flood's hydraulics allowed. The environmental implications of these debris fields extended beyond immediate cleanup challenges. Petroleum products, household chemicals, and industrial materials mixed with floodwater and sediment created contaminated zones that required assessment before safe reoccupation. Biological hazards emerged as organic material in the debris began to decompose in the June heat. Agricultural impacts appeared downstream from the city, where the flood deposited debris and sediment on farmland adjacent to the creek. Fields received layers of mud, sand, and urban debris that would require removal before agricultural operations could resume. Irrigation infrastructure was damaged or buried. Livestock that had been in flood-prone areas sustained losses measured in hundreds of animals. Floodwaters began their gradual recession during the early morning hours of June 10, though the withdrawal occurred over many hours rather than minutes. As rainfall over the Black Hills finally diminished, inflow to the creek system decreased. Water that had spread across the floodplain began to drain back toward the main channel, following topographic gradients and the paths of least resistance through debris-choked terrain. The pace of recession varied across the affected area. The main creek channel, with its continuous downstream gradient, drained most rapidly. Tributary channels and smaller waterways followed. Low-lying areas with poor natural drainage retained standing water for days, creating isolated pools that required pumping operations before they would clear. Mud coated virtually every surface that had been inundated. Streets, sidewalks, building exteriors and interiors, vehicles and vegetation all bore layers of fine sediment that had settled from the floodwater as it receded. When wet, the material formed a slick, clay-like texture that made movement slow and hazardous. As it dried over the following days, it formed a dense crust that necessitated scraping and mechanical removal. The creek itself returned to a recognizable channel, though its characteristics had changed. Banks were scoured in many locations, vertical faces cut into alluvial deposits that had been stable for decades. In other areas, new deposits of gravel and coarse sediment had accumulated, altering the flow path and eliminating familiar bends. Survey crews documented these changes systematically, mapping the modified channel so that future floodplain planning could account for its new geometry. Debris fields became focal points of early recovery operations. Piles of vehicles, house fragments, trees, and metal had collected at natural constriction points in the valley. These accumulations obstructed movement and posed risks to both workers and equipment. Clearing them required cranes, winches, and teams of workers operating in shifts. In some cases, the debris measured tens of feet in depth. As access routes reopened, assessment teams moved through affected neighborhoods. Structural integrity inspections determined which buildings could be repaired and which required demolition. Utilities crews evaluated water, gas, and electrical systems, many of which had been compromised or destroyed. In areas where bridges had failed, temporary crossings were installed to restore movement across the creek. Public health considerations shaped much of the initial response. Stagnant water and contaminated sediment required disinfection measures. Wells were tested. Instructions for boiling water were repeated in daily broadcasts. Medical facilities operated around the clock to treat injuries, infections, and exposure-related conditions. Vaccination programs were initiated to prevent disease outbreaks commonly associated with large flood events. Long-term recovery planning began almost immediately. Officials from municipal, state, and federal agencies documented the sequence of failures that had contributed to the scale of destruction. Recommendations included revised zoning regulations, increased setbacks from waterways, improved dam safety protocols, and investments in early warning systems. These proposals reflected a broader recognition that rapid creeks hydrology, when combined with extreme rainfall, posed risks that had previously been underestimated. In the weeks following the flood, the visible signs of disaster slowly diminished. Mud was removed from streets, businesses reopened in limited capacity, and utilities were restored. Yet the landscape retained indicators of the event: eroded banks, altered channels, damaged trees, and empty lots where structures had once stood. The physical environment of Rapid City had been reshaped, its patterns of water and land permanently altered. As summer advanced, the Black Hills returned to outward calm. Pine forests resumed their characteristic stillness, and the creek flowed within new boundaries cut by the flood. The sound of water was once again familiar and unremarkable, but beneath that surface quiet, the record of June 1972 remained embedded in engineering reports, revised planning documents, and the altered topography of the valley. The flood receded completely, yet its imprint persisted, a silent ledger of the night when the hills released their water.